Life is chaos. The whole universe is chaos, whether it's the terrible state of my office or the slow degradation of my body into dust. The universe tends toward disorder. But why? Why is the universe structured in this terrible and callous way? Well, it turns out it's not really the universe's fault. If you think about it, there's only one way, or at best maybe a few ways, for things to be arranged in an organized way. But there are nearly infinite other ways for those same things to be arranged. Simple rules of probability dictate that it's much more likely for stuff, whether it's the stuff on my desk or the particles and energy that make up my concept of self, to be in one of the many disorganized states than in one of the few organized states. It's simple math, and it's unavoidable. So unavoidable that it is, in fact, our second law of thermodynamics, which says that any spontaneous process increases the disorder or randomness of the universe. Processes that don't increase the disorder of the universe require work to be done in opposition to the disorder, and are, in fact, often impossible to achieve. The very act of putting one system in order requires that other systems become disordered. Think of it this way. Your lunch was composed of an extremely ordered set of molecules, and it gave you the energy to clean up your house, maybe. And it had to be broken down into less ordered nutrient molecules for you to do that. Carbohydrates, proteins, and lipids, and those molecules were broken down even further as they were converted to energy in your cells. And then your body used some of that energy to power your muscles as you cleaned your house. But much of that energy was used to do things like keep your heart beating and breathe and make sweat. And some of that was lost to the surroundings in the form of random movement, and most importantly, heat. By the time you finish, your house may be orderly, but the remains of your lunch molecules are all over the place. And that's only one of the many systems that became less orderly while you worked. So yes, cleaning your house, in fact, increased the overall disorder of the universe. Next time someone gives you a hard time about the state of your house, you can tell them that. Obviously, disorder is a pretty big deal in the universe, and that makes it a pretty big deal in chemistry. So scientists have a special name for it: entropy. Entropy is a measure of molecular randomness, or disorder. And even though people complain about the disorder in their lives, it's not all bad news. Entropy helps make chemical reactions possible, and it helps us predict how much useful work can be extracted from a reaction. We all have to live with disorder, so you might as well understand it. For the next 10 minutes, I want you to embrace the chaos. So what does the second law of thermodynamics mean when it says any spontaneous process increases the disorder of the universe? Spontaneous simply means a process that doesn't need outside energy to keep it going. And it goes the other way too. Anything that increases the disorder of the universe happens spontaneously. That doesn't mean disorderly things will always happen, though. Other factors may interfere. The reaction to change a diamond into graphite, for example, would be thermodynamically spontaneous. It wouldn't have to be forced along by outside energy. But the bonds in the diamond are so stable that essentially it never gets started. Lots of other chemical reactions are like this too. So even though we sometimes think of spontaneous as meaning sudden and impulsive, like the majority of mall lip piercings, in chemistry, spontaneous doesn't tell you how quickly something happens. It only means a reaction is thermodynamically capable of happening without outside energy to move it along. Though come to think of it, I imagine that spontaneous lip piercings cause a fair amount of disorder as well, especially upon arriving home. Entropy is another state function. It doesn't depend on the pathway the system took to reach its current state. So even though we can't measure the entropy of reactants or products directly, we can calculate them. We can also calculate the change in entropy that occurs during a reaction, exactly like we can for the change in enthalpy, by subtracting the sum of the reactant values from the sum of the product values. In other words, the formulas look exactly the same, just substituting S, which for some reason is used to denote entropy, for delta HF. Notice that we drop the deltas on the right side of the formula because we know absolute values for entropy of individual reactants and products. We keep the delta on the left because we're calculating the change in entropy that occurs when the reactants rearrange into products. What the heck is this good for? Well, we can explain a mysterious thing, which is how reactions occur spontaneously in nature even though there's no energy given off, or even they suck heat out of the environment and seem to go up the energy ladder instead of down. Let's try it out with a real reaction here on my desk. This is one of my favorites. This is barium hydroxide octahydrate, and this is ammonium chloride. Usually, we do chemical reactions in aqueous solution because most solids don't interact easily, but this pair is an exception to that rule. They react readily in solid form. And this reaction absorbs a lot of heat from the surroundings, making everything around it feel cold. Now, to show you how cold it gets, I'm going to do something here. You're just going to have to assume you understand what I'm doing. What am I doing? What is happening? Why am I doing this? That's weird, Hank. Why are you doing that? And then I'm going to put that on there. So I've got my barium hydroxide in this beaker. Now I'm going to dump the ammonium chloride in. And now one of the byproducts of this reaction is ammonia. So I'm going to have to smell that, but you don't. Oh yeah. Look at that slush. I think we've reacted pretty much completely here. And so we should, if all things have gone properly, yep. That's pretty cool. Sucked enough heat out of the block of wood to actually freeze it to the beaker. In the world of chemistry, a reaction that proceeds spontaneously and yet absorbs heat is really weird. Basically, I have a hard time believing what I just did. So what does entropy have to do with this little freak show? You might think it has something to do with taking the heat from the surroundings to make the system colder, but while that's counterintuitive and cool, that's not all of it. You might also think that it has to do with two solids combining to form a whole bunch more liquids and gases, and that is a big part, but still not all.
I'm going to pick up where I left off in that podcast that you watched that got a little bit truncated. So the thing about the third law is that it says that the the entropy of a perfect crystal is 0 at 0K. The usefulness of that is that S of an element is not 0. Unlike H, and when we get to Gibbs-free energy, H and G, they are 0. So S for an element is not 0. And that's because elements have electrons, and as long as you have electrons, you can be disordered. Okay? So S will always be greater than 0 for an element. Okay. It's kind of like this. It's kind of like a probability model. So if I have 4 particles, there's lots of just 4 particles, and I've got 2 bulbs on my gas container. It is possible that all 4 would be in one bulb or the other, right? But it's more possible that 3 of them will be in one and 1 of them will be in the other, right? Okay? But the thing that's most possible is that 2 will be in one bulb and 2 in the other. And there are lots of possibilities for how that arrangement occurs in terms of whether the red or the blue are together or the green and the yellow. Okay, so this is just an issue of probability. So what's most likely is the most disorder, the most spread out. Okay? All right, so that's the idea behind it. So the greater the dispersal of matter or disorder or spread out or less condensed in a system, the larger the entropy. Okay? The entropy always increases as it changes from solid to liquid to gas. Because as you can imagine, the gas is just much more spread out, much more disordered. You know, a solid is very ordered, you know. Particles are nice, neat, lattice work. Okay, so when a pure solid or liquid dissolves in a solvent, as you can imagine, you're going to have these particles in a solid that are nice and neatly organized, and a liquid that is pretty well organized. You know, think about water. It's got hydrogen bonds, and it's pretty well ordered. When you mix the two together, you end up with separating all of those particles, and now they are just much more spread out, and entropy increases. Now, there are a couple of exceptions to that, carbonates included, but for the most part, if I dissolve something, my entropy increases. Okay, if a gas molecule escapes from a solvent, entropy increases. It flies off into space, right? There's lots of different places that that particle can be. Okay, so entropy generally increases with increasing molecular complexity. Okay? And this is because there are more moving electrons. Okay? So the more atoms I have, the more electrons I have. The larger the atom I have, the more electrons I have. And the more electrons I have, the more disorder I have. Okay? So when I increase the number of moles of particles, I increase entropy. So if I start off with reactants going to products, and I have, let's say they're all gases, and I start with 2 moles of reactants, and I end up with 3 moles of product, my entropy goes up. Okay? Now you really can't just compare going from a gas to 3 liquids, but within a state of matter you can. If you increase the number of moles, the more stuff you have, the more possible arrangements you have. So the greater the number of arrangements, the higher the entropy of the system. Let's see what we can predict. So as I do this, I want you to make a prediction. Alright, so solid sugar is added to form a solution. If I do that, my entropy will go up. Okay? Iodine vapor condenses on a cold surface. My entropy will go down. If I do C, let me see. I'm going from a solid to a solid, a liquid, and a gas. My entropy is going to go way up. Here I am going from I have all gases, right? So I'm going from 2 moles of gas on the left with hydrogen 1 here, so that's 3, to 2 moles, my entropy goes down. Here, now I forgot to put in here that these PCl5 and PCl3 are solids, so I'm going from a solid to a solid and a gas, making my entropy go up. Okay, so I can calculate entropy from standard table of standard values, just like that reference pack I've been giving you. There are entropys on there. Just be careful. Again, units for entropy are joules per mole Kelvin. Okay, so there is a temperature component to entropy, and it is not in kilojoules. They're not reporting kilojoules like enthalpy in Gibbs energy are. Okay, so be careful of that. Alright, so here we have a problem, and we want to calculate the total. SO2 plus O2 becoming 2SO3. So the change in entropy is going to equal the sum of the entropy of the products minus the sum of entropy of the reactants. So the products is going to be 2 times SO3's value minus 2 times SO2 plus O2's value, 1O2, right? And important thing here is that the entropy of the elements is not 0. So I'm going to have 2 times 256.6 minus 2 times 248.1 plus 205.3, and when I plug in, I chug, I get minus 188.3 joules per mole K. Okay. So summary here, if my S is positive, I have more dispersal. It's a more favored, thermodynamically favored condition. If I have S that is negative, I have less dispersal. Okay, so if S is increasing, that is favored. And we'll talk more about how to determine whether a system will be spontaneous or not when we get to the next section. Okay, that's going to do it for us.